Last video, we discussed the free particle, so potential zero everywhere, and we looked at unbound states of that free particle, and we realized that we tried to solve the energy eigenvalue equation, and what we saw was that the energy eigenfunctions were shared with the momentum operator and the momentum eigenfunctions. Today, what we're going to do is we're going to continue to look at these free particle examples. We're going to look at superpositions in momentum space, which is generally how we can look at free particles. So to recap, these momentum eigenfunctions that we solved for last time look like this, right? They had eigenvalues of h bar times k, that wave vector, and that actually led us to the de Broglie relationship for the wavelength of a free particle. Um, and the momentum, though, is a continuous variable, right? The fact that there were no boundary conditions due to some well that that would quantize that wave vector, we just have a continuous set of momentum eigenfunctions. And that meant we needed to treat them sort of the same way we treated the position eigenvalues and eigenfunctions. So if you recall, the general position space wave function looked like this, and we can actually write it in terms of it's the Fourier transform of the momentum space wave function that looks like this. So what are we actually looking at here? So the position space wave function, if you remember, is essentially the sort of the probability amplitudes of that particle you're describing being found at that position x, and it's a continuous function of x because x is a continuous variable that you could measure the position of a particle at. Likewise, if we go to momentum space, the momentum space wave function is the same sort of thing. It's the probability amplitude of having that particle have a momentum of value p, and because p is a continuous variable, this ends up being a continuous function rather than a bunch of discrete coefficients in a linear combination. But they are actually the Fourier transform and the inverse Fourier transform of each other. Um, and if we want to actually represent the proper a free particle correctly, we need that position space wave function is actually going to be a Fourier superposition of the momentum eigenstates, right? So this uh, momentum space wave function, like we said, is the probability amplitudes of finding that wave function at a given momentum eigenstate. And we know those momentum state eigenfunctions. So this is essentially the one way we can think of it is it's like those linear expansions in a given basis we're familiar with from our Dirac notation. The the momentum space wave function, this 5p here, amounts to being like analogous to the coefficients in that expansion, and the eigenfunctions are just the momentum space eigenfunctions, but instead of summing over a bunch of discrete states, we're doing an integral over a continuous set of states here. And that's what we're going to work on today, and how we can look at these momentum space representations or superpositions and what they mean for free particles. So we're going to start with a bit of a simplification to kind of map it to what we're more familiar with. There's some problems with normalization and things like that with this, but it's a really good way to go about getting sort of a qualitative feel of what's going on here. So we're going to consider a discrete superposition of three momentum eigenstates with different amplitudes. One at the momentum eigenvalue p naught, one shifted a little lower by some delta p, and one shifted a bit higher at delta p. And we're going to have different amplitudes in the superposition. So the eigenfunction for the central momentum p naught is going to have twice the amplitude of the two shifted by plus or minus delta p. So our discrete superposition, if we were to plot those coefficients or our momentum space wave function, rather than being some continuous function like this, we just have those discrete amplitudes at those points, like we thought of way back when we started with just spins in the discrete spaces. So what happens when we actually look at that superposition, right? So we know that the eigenfunctions have this form, and if we plug in the momentum eigenvalues that we're looking at, p naught, we have twice the amplitude as the other one. We're looking at just the real part here, but the imaginary part's going to look very similar. We have that oscillatory wave function. If we look at the one that's shifted to a slightly lower momentum value, the wavelength's going to be, slightly longer because they're related to that de Broglie relationship. And the one shifted to a little slightly higher momentum value is going to have slightly shorter wavelength. And so these are the two individual momentum eigenfunctions we're adding together to get this superposition state of our free particle. If we actually look at that superposition state, we're just adding them together. We get this destructive and constructive interference, right? So if we look right here along this line, all three of our momentum eigenfunctions have a maximum there. So we're going to have constructive interference and make a maximum, but at some, distance in space away, some delta x, because of the difference in wavelengths, because they all have different momentum values, we have, a minimum here and a minimum here and a maximum here. They all destructively interfere, and we get no amplitude here. And what we've essentially done is make this sort of wave packet through the interference between the superposition of all these momentum eigenfunctions that's resulted in sort of a localization of this free particle. And if you recall in our last video, one of the problems with these, or the difficulties with these individual momentum eigenstates is that they have finite amplitude everywhere, so they weren't really normalizable. And if we're talking about a free particle, we would expect it to be localized in some way. This is sort of gives you an idea of how that comes about by the free particles are in superpositions of these momentum eigenstates. So what are we going to do with these? Let's look at our time dependence, right? So what was the way we treated time dependence previously? Well, we took our generalized wave function or state function at t equals 0, wrote it in the energy eigenbases, which is shared with the momentum eigenbases. So we write it in the momentum eigenbases, and then we're going to add phase factors. So if we take that superposition of our three momentum energy eigenfunctions, the two have had half the amplitude of our central eigenfunction, we get this. That is our wave function at t equals 0, and it's written as a superposition of our momentum eigenfunctions. If we want to add the time dependence, we simply add these three energy sort of dependent phase factors like we did in our previous studies of time dependence, right? And we know the energies of these eigenfunctions. If you recall, the energy of a momentum eigenfunction for our free particle is just the momentum eigenvalue squared over 2m. So plugging in the momentum eigenvalues for our two functions we're adding together here, we get this. That's what we have. If we substitute those into our wave function and expand those squared terms, we end up with this, right? So again, all we've added is those energy phase factors to our superposition states. One thing we're going to do here, though, is we're going to, just for the sake of this discussion, we're going to assume that our central momentum eigenvalue is much greater than sort of how far the other two are shifted from that central momentum eigenvalue. And that's going to allow us to get rid of these two delta p squared terms, giving us our time-dependent wave function looks like this, right? Now that we have it written like this, we can just do some simplification and some factoring and whatnot. If we factor out this term in the middle here, we end up with this, right, is what's left. And this can be really simplified by noticing that well, first, we can take the term outside the brackets and simplify that exponent, and likewise the exponents inside the bracket just by factoring out a p naught over h bar outside the brackets, and inside those square brackets a delta p over h bar to get this. And this can be simplified by acknowledging that those exponential terms inside those square brackets are actually, that's cosine. That is the exponential form of cosine. So all of this simplifies to our time-dependent wave function looking like this. Um, so this is really interesting, and it really shows how we had that sort of localization, because there's essentially two parts to this waveform, and both of them have the form of a wave, right? They're a function of some variable x plus some constant times t, right? The first term we call the carrier wave, and you'll notice it's sort of characterized by that central momentum p naught. So it has a wavelength associated with it of h over p naught. And its velocity is what we call the phase velocity, and it's p naught over 2. It's that constant that is multiplied by the time. If we look at the other term inside, that is the envelope sort of part of our wave function, the envelope wave, and it modulates that carrier wave, and it's characterized by this delta p out front. So it has a much larger wavelength because delta p is shorter, of h bar over delta p, and its velocity is different. It moves at what we call the group velocity, that is just p naught over m. That's actually the velocity we would expect classically, right, in our classical physics. So what this looks like is the carrier wave are those short wavelength fast oscillation parts inside that broader envelope outside. So we have our envelope with a longer wavelength, looks like that, and our carrier wave inside with the shorter wavelength. And they move at different velocities, right? Uh, One moves at twice the speed of the other. So the wave, the sort of inside carrier wave, moves at half the classical velocity, and the envelope moves at the classical velocity, what we call the group velocity. And you can see that in this animation. So the blue dot is going to be the envelope's velocity, if you follow that, and the black one's going to be moving at the carrier wave velocity. And you'll see the packet, the actual localized particle, is moving at the group velocity, which is why we typically use that to describe how fast a particle is moving. So if we want to just look at that again, we see the group velocity moving with the whole envelope and the sort of localized packet, while the phase velocity moves at a 1/2 that speed, much slower. And this is sort of why we look at the group velocity as the appropriate one to use when describing how fast a particle is moving. All right, so this was a nice sort of example that kind of hopefully gives us a bit of intuition and thought of what's going on in these superpositions and how it can help us with some of the issues. But we still haven't actually got through any of our issues, right? If you remember, one of the problems was these weren't really normalizable eigenfunctions. They had probability, they had amplitude everywhere in space, so they couldn't really be normalized. We've sort of hinted at how we can get around that, but because we're still only using a discrete superposition when we're in a continuous, sort of eigenvalue bases here, we still have that same issue. We have a chain of sort of localized wave packets, and it's still not really normalizable. What we actually have to do is look at continuous superpositions if we want to treat this properly. And in that case, what happens? Well, this discrete sort of superposition that we've used, rather than using these, discrete coefficients, we're going to, and summing over all of them, we're going to integrate over that momentum space wave function. And that's going to give us our continuous superposition of our momentum space eigenfunctions, or our momentum eigenfunctions. Uh, so again, with the time dependence, this is what our wave function looks like at t equals 0. Subbing in that value, what we know the form of our momentum space eigenfunctions are, or sorry, our momentum eigenfunctions are. It's actually in position space. We get this. If we add that time-dependent phase factor to get our time dependence on this, and then the value of what that energy is in terms of the momentum, we end up with this, which we can again simplify to sort of show how that term is actually has the form of a wave. Um, and we get this as our time dependent wave function that is a superposition of those momentum eigenfunctions. To actually use this and look at an example, we need to know what that momentum space wave function is. We need to know what this 5p is. What are those, it's the equivalent of what are the coefficients that are making up that superposition. Um, so what we're going to use is we're going to look at a case where it's a Gaussian distribution, a probability distribution of those eigenvalues. So just a quick refresher on Gaussian distributions. A Gaussian distribution has the form of this, right? Where we have 1 over sigma root 2 pi e to this, and the mu is what we call the mean. That classifies with the mean. It's where the distribution is centered at. So if you look at this blue curve, it's centered at 0. That's where the peak is. The sigma is the standard deviation. It's essentially the width of that of those peaks, or the width of the distribution. So again, these three that are all lined up at mu equals 0. As we, the blue one has zero point 0.2 is its standard deviation, the width. As we make it bigger with red of 1 and the green one of 0.5, that peak gets broader and broader. And if we, the other peak here, we've shifted that average to -2, so it's there. So hopefully you're all sort of familiar with this. It comes up a lot, and it's a proper way to treat a lot of situations in physics in that. In general, the mean is going to be our expectation value for that variable, and the standard deviation is our uncertainty in that variable, which will come up later. So this is Gaussian distributions. Let's consider the case where the probability distribution of our momentum is Gaussian distributed. So i.e. the probability of measuring that particle with that given momentum is Gaussian distributed, centered at some central momentum p naught, and has some width of beta. What that means is, so that's the probability distribution, again, with those values. What that means is our actual momentum space wave function is the square root of that and looks like this, right? So we have a Gaussian distribution in our momentum space. That means we can plug that in to get our position space wave function as a function of time. So again, all we're doing is plugging this in to that equation. So we have our momentum space wave function. We have this term, and that term is the position dependence of our momentum eigenfunction, and then the time dependence because we plugged in that energy dependent phase factor there. If we just do some math on that, we expand that exponent, that p minus p naught squared term, we get that. We can, bring all those exponents together. Do some rearranging, take all the terms with a p squared in them, all the terms with a p in them, all the terms without any p in them, and sort of factor them out. We get it in this form. This last term without a p, we can bring outside of our integral because it doesn't depend on any of the what we're integrating over. And now we have our wave function as a function of time, and we have it in a convenient form because what we're integrating over is actually a Gaussian integral. And You can look this up from a table of integrals, or there's one at the back of the book in Appendix F. It's actually equation F23 that, we have this a in our exponent and this b in our exponent, or a squared, I should say. Uh, and so we can just essentially we can do this integral, and it takes a while. I'm probably going to assign it in the homework for you to go through it. But the gist is, after a bunch of simplification and defining some new parameters, that gives us our position space wave function, our wave function as a function of time as well, uh, of this form, right? Where we've defined gamma and tau this way. We can also define another term, alpha, which has to do with, it's going to be convenient later on because it has to do with it makes it look more like a Gaussian. It makes it easier to identify what the width of this probability distribution will be in position space. But for now, we define an alpha like this, and our time-dependent position space wave function looks like this, right? And again, it has two parts. It has this carrier wave part that is characterized by this momentum p naught and has a phase velocity of p naught over 2m, which is half the classical velocity we would expect. And we have the envelope that is characterized by the width of our probability distribution, the width of our distribution in momentum space, beta. It might not be obvious here, but this alpha over here is inversely related to beta. So this is actually characterized by that beta. And it moves with the group velocity p naught over m, which is what we'd expect classically. So again, we have by having a superposition of these momentum eigenstates, we end up with sort of these two types of waves, a group that sort of localizes an envelope that sort of localizes this particle in space, and then a carrier wave sort of that's modulated by that envelope. Right. So we have that. Now we can look at the probability density in position space representation. So what is the probability of measuring this particle at some position? Well, that probability density is just that wave function, the amplitude of the complex square of that. And if we take that, this term with the imaginary exponent becomes 1 when you take that, multiply it with its complex conjugate. So we're left with just this, right, where we've redefined this capital gamma as the magnitude essentially of that lowercase gamma. And it has a time dependence to it. So this probability density, though, if you see, it looks like a wave as well. And it moves with the group velocity, right? This x minus p naught over mt takes the form of a wave where the function maintains its shape but just moves with that group velocity. And again, that probability distribution is moving at the group velocity. So again, this is why we use the group velocity to describe how fast a particle is moving. So what that looks like, right? If we take the real part of our position space wave function, we have the carrier wave with these fast, short wavelength sort of oscillations, and the envelope function that localizes at that. And this, because we're doing a continuous superposition, doesn't actually have a train of another one. It actually does localize that, so it is now normalizable, and it's sort of solved the problems and the issues we had before. The probability distribution of that is actually Gaussian, and looks like this, but does move, as we'll see. It moves with this group velocity. So now that we have our probability density and position space in that, we can start to look at expectation values, right? It's things that are going to be relating to our measurements in that. So our position expectation value is just going to be, the integral over all space of x, that position operator, times the probability density. And just by inspection, we can see it's going to be the sort of the mean of that probability density, wherever that average is going to be, and that's P naught over M times T. That mean of that Gaussian distribution moves with that velocity. Likewise, if we want to know the momentum expectation value, we can do that in momentum space, and we get the momentum operator times that probability distribution of our in momentum space. And if we just look at, again, we can go through all that math, or we can just, be clever about it with the inspection. If we look at that momentum space wave function, we made it, that was in a Gaussian form. So that probability distribution is, again, Gaussian, and its average value is going to be centered at P naught, the what that central momentum eigenvalue was. So that expectation value is just P naught. We can do the same sort of thing with the uncertainties, right? If we look at the uncertainty in our X, it's going to be related to what is, if we look at the sigma in the Gaussian distribution, that's alpha gamma here. And likewise, in the momentum distribution, it's just beta. So we know that those uncertainties from these two distributions are alpha gamma, which is equal to that using our definitions of alpha and gamma. And in the momentum, our uncertainty is just beta. And it's worth, mentioning a few other things on this is if we look at the momentum properties, it is a Gaussian distributed probability density with an average at P naught, that central momentum eigenvalue, and standard deviation of beta, but it's constant in time. That doesn't change. There's no time dependence in that distribution there. Whereas if we look at the position this probability distribution function, that average, that mean, moves with the group velocity and has a standard deviation of alpha gamma. So that average sort of expectation value for a measurement of the position of this particle is going to move the same way we would expect it classically with a velocity of that momentum over m, that group velocity we've discussed. But one thing that is also worth noting, it broadens as a function of time. That standard deviation has that time dependence in it. So as time evolves, as we go further and further on, that distribution is actually going to get wider and wider and wider and broader, right? This, if you think about this in terms of waves, classically, that sort of makes sense, right? We have this wave packet made up of a bunch of different superpositions of waves with different momentum. So some moving a bit faster, the others moving a bit slower. So it's slowly going to spread out. Like if you imagine a group of people all running, and some are faster and slower, as time goes on, those people are going to be spread out more. Same sort of thing with this wave packet. Some of the waves that are making it up are moving faster than others, so it spreads out over time. However, that's not what we would expect for a classical particle, right? We're trying to describe a free particle. Classically, a particle is localized and it moves through space with some set speed or some momentum, and it's going to have that the same size, or it's going to be localized in the same way as it moves through space. In quantum mechanics, what we're seeing here is it's actually broadening as time evolves, and it's so it's a little counterintuitive here if you try to think about this in a purely particle sense. But that's sort of the gist for today's lecture. We fixed sort of some of the problems we had in our previous video, where we were discussing the momentum eigenstates and how they weren't normalizable, and those sort of things. If we actually look at continuous superpositions of those to get our wave functions, we sort of solve that problem. It ends up forming wave packets that are localized in space, they're normalizable, and we just look through what we expect for different expectation values in that. But before I end the video, I just want to spend another brief second talking about group and phase velocities. It comes up, quite a, it's one of those things that comes up in a lot of courses, but it's not really central to a lot of courses. So they all just kind of talked. Spoken about in optics, I think is where it comes up the most. And is sort of defined as the phase velocity of a bunch of waves is, or the phase velocity is that, angular frequency divided by the wave vector, and the group velocity is the derivative of that angular frequency with respect to that wave vector. In quantum mechanics, we have, the relationship that the energy is h bar omega. We used that a few times already, where we, wrote that energy over h bar in terms of an angular frequency. And we have the momentum as h bar k. So, sort of mapping that, we can throw in an h bar over h bar in both of these phase relationships, and that gives us this, where our phase velocity is just the energy divided by the momentum, and if the energy is p squared over 2m, that gives us our phase velocity of p over 2m, just like we got, and the group velocity ends up becoming the derivative of the energy with respect to momentum. And if we take that derivative, we just get the momentum over the mass, which is the same as we had classically. Uh, Again, why these have those names has to do with what's actually moving, right? Um, if we look at the group velocity, it's how fast the packet, the whole group of waves, is moving through space, whereas the phase velocity is how fast sort of that one crest is moving, or how fast a point of constant phase in the short oscillations is moving through space. Um, anyway, if you're taking solid state physics this semester, or if you take it in the future, that will probably come up there. It will definitely likely come up in optics courses and in a few other places, but hopefully you can get comfortable with that. Again, as usual, if you have any questions, please don't hesitate to reach out to me, and I will see you in our synchronous sessions.